Hello everyone, I'm here to give a video presentation with my friend Jay about topic synchronizers. I'll start with the presentation. Synchronizers. Most distributed systems and its components are asynchronous to each other. A synchronizer is a protocol that transforms asynchronous model into a synchronous model. It enables synchronous algorithm to run on it. But why do we care? Why do we care about synchronization so much? It will be clear and it will be easier for us to realize if we take some analogy. Let us consider watches. We all wear watches in our wrists, and our watches are synced to a certain standard time. Let's say a person at France is trying to send a message to us here at US. So if he says that he will be sending a message at 1:30, then if our watches are synced with the person at France, then we'll expect to get the message at 1:30. But if our watches are not synced, then his 1:30 will not be our 1:30. So it would be very difficult for us to figure out what exactly is the time that we are here to receive the message. But if he says, for instance, that he'll send a message at 1:30 GMT, then we can have a synced clock with the person at France. So we can expect the message to be sent at 1:30 GMT. So the communication here becomes easier. So we use synchronizers because asynchrony is hard to deal with. Asynchronous algorithms are complex in design and analysis are much more complicated. It is helpful to develop a general simulation technique that will allow users to write an algorithm as if it were run on a synchronous network. The synchronous algorithm, what is it? A synchronous algorithm runs in discrete steps known as clocks or ticks. In each tick, the clock processes a local computation and sends out a message to neighbors and receives message from its neighbors. How synchronizers work? Let us assume that each node has a clock pulse generator and this clock ticks in unison. The condition that a new pulse should be generated at a node only after it receives all the messages of the synchronous algorithm sent by the node at the previous pulse should be satisfied. It basically means that a new message is sent for the next tick only when all of the message for the previous tick has been completed. What are the problems associated with it? One of the limitations is that it is difficult for a node to know which message is sent by which neighbors. And the message propagation delay can be arbitrarily large. So once a process sends a message, it waits for an acknowledgement of the received message. But since the message propagation delay can be arbitrarily large, the waiting can be arbitrarily large. And the node just waits and waits to send the next message. Types of synchronizer. ABD are asynchronous bound delay synchronizers. The Auberg synchronizers, there are three synchronizers under it. These are alpha synchronizer, beta synchronizer, and gamma synchronizer. They are classified based on their complexity, the message complexity and the time complexity. We'll discuss these synchronizers later in our slides. The asynchronous bound delay synchronizer. The asynchronous bound delay synchronizer works on the assumption that every process has a physical clock and the message propagation has a known upper bound delta. Message propagation delay has a known upper bound delta. The difference between the physical clocks does not change over time during the computation. The asynchronous bound delay synchronizers is not that practical, because it assumes that the difference between the physical clock does not change over time. However, in practical scenarios, even synced processes tends to drift apart in time. Um, how does ADB works? Let's see denote a physical clock of a process. The synchronizer action is initialized by one of the process by assigning C to 0. Action of that tick C0 is performed and a message is sent to all of its neighboring nodes. The neighboring nodes sends its own message and also sends an acknowledgement for them. The neighboring node sends its own message and to its neighboring nodes as well, and this completes the initialization process. Here is a diagram, a pictorial diagram of how ADB works. Let us consider 4 nodes, 0 and 1, 2 and 3. Let us consider node 1 and node 3 initialize automatically. So 1 and 3 send start signal to its neighboring nodes, to its non-initialized nodes, that is 0 and 2. 0 and 2 wakes up after initialization and sends its corresponding message to its neighboring nodes, that is 1. What are the limitations of ADB synchronizer? As we've discussed, it cannot be used when the physical clocks are not synchronized or the upper bound delay of the message propagation is not known. To overcome this limitation, we have the Auburg synchronizers. The main idea is to determine when the process is safe to schedule the action of the next clock tick. In the ADB synchronizers, as we've seen in the previous diagrams, it depends on the message propagation delay. So let us consider node 1 and 2. 1 sends message to 2 with a propagation delay of delta. Similarly, 2 sends a message to 1 with a propagation of delta. So considering just node 1 and 2, node 1 can send the message for the next clock tick after a time delay of delta plus delta, so the time anywhere greater than 2 delta. So node 1 can now send a message for the next clock tick at a time greater than 2 delta. But when message propagation delay is not known, ADB synchronizers cannot be used. But Auburg synchronizer does not need message propagation delay. Instead, it uses a safe message signal to schedule the action of next clock tick. A process is safe to send a message for a given tick when it has received an ACK for every message that it has sent, its neighbors have sent out their message for the current tick, and a safe process announces this by sending a safe message to its neighbors. A violation of this property will violate the property of synchronizers. Again, these are the types of synchronizers here: alpha synchronizer, beta synchronizer, and gamma synchronizer, each with a different strategy for using topological information and detecting safe configuration. Now let us discuss alpha synchronizer. In alpha synchronizer, each process executes the following 3 steps: sends and receives message for a current tick, sends acknowledgement for the current tick, and sends a safe message to its neighbors. Once it receives a safe message, it can then go in and perform actions for the next clock tick. Here's a partial trace of execution of a synchronizer. Let us consider 6 nodes as shown in the figure. Here, the number in the nodes denote the action for the current clock tick. So here the first node, it initializes itself to 0 and sends its message to its neighboring nodes. The 2 nodes, after receiving a message from the first node, gets initialized to 0 as well, and it sends an acknowledgement to its previous nodes. of receiving a message. It also sends its own message to its neighboring nodes. Similarly, the two nodes at the bottom, it gets initialized after the message is sent, and it also sends a message, an acknowledgement to the previous nodes. Once all of the message has been sent and the acknowledgement has also been received by the first node, it then sends a safe message to its neighboring nodes. Is the safe message after receiving acknowledgement and the message from other nodes. Similarly, the safe message is sent by the neighboring nodes as well to their neighbor nodes, and when all of the nodes sends the safe message, then the first node can now send message, the next message for the next clock tick, that is clock tick 1. So it initializes itself to 1. The complexity. While dealing with synchronizer, we generally consider two types of complexities: the message complexity and the time complexity. The message complexity is the number of messages passed around the entire network for a clock tick. The message complexity for the alpha synchronizer is O of E, where E is the number of edges. The alpha synchronizer is considered to have a high message complexity. This is because of the characteristics of alpha synchronizer. We'll go back to the slide. Each process should execute the following 3 steps in an alpha synchronizer. Send and receive messages for the current tick I. But what if the current node does not have any message to send? If it does not have any message to send, then it will send a blank messages. So for example, if we consider 3 nodes, node 1 sends a message to node 2, and node 2 does not have any message to send, then node 2 will send blank messages to its neighbors. Until and unless it sends some messages to its neighbors, node 3 cannot initialize itself, and node 1 will not send a safe configuration, and there is no way of moving forward to a next clock tick. So that's why the message complexity of alpha synchronizers is high. The time complexity. The time complexity is given by the number of synchronous routes required by the simulator for each clock tick. Since each process exchanges 3 messages, T alpha equals 3. And what are the 3 messages that each process sends? The first one is the message, the original execution message that it needs to send to the other process. The second one is the acknowledgement, that is, had received messages from the previous node. And the third message is the safe message that it needs to send so that it can move forward to sending messages and executing computations for the next clock tick. Now we have a beta synchronizer. And the beta synchronizer will be discussed by my friend Jay and compare it with alpha synchronizers, and he will conclude the presentation. Thank you.